So converting units is a very important topic in science and engineering that we need to master. And the aim of this podcast is to help you practice and master it. So it's made up of various questions. The first one gives you certain quantities, 1, 2, 3, 4, 5, 6 of them, and the idea is for you to work them out in terms of the SI units, so in terms of meters, in terms of joules, etc. And that's something that I hope you can essentially just write down. The next question is to calculate these quantities in these units. The next question is a two-step problem, and it's to express a density given in these units, to express that in these units. And the final question is based around something called Young's modulus, and there is a formula for it here, and here are these quantities, and you are supposed to calculate Young's modulus and to express your final answer in gigapascal. So with that, I think you should pause the video, work out the answers on paper, and then come back and see if you've got them right. Okay, welcome back. Let's look at this question on the next slide. So in the first question, we were asked to express these quantities in terms of the fundamental and derived units, and let me just write down the answers for the first lot. So what we have for the first one is that a millimeter is 10 to the minus 3 meters. So what we have here is this is 3 times 1 millimeter. You don't necessarily need to write that step down, and that is 3 times 10 to the minus 3 meters. So if you're confident that you're not going to get it wrong, you can go straight from there to there. But this is what's happening. The next is 6 megajoules, and a mega is a factor of a million, so this is going to be 6 times 10 to the 6 joules, and that is our answer. The next one is 2 nanowatts, and nano is a billionth. It is 1 divided by 10 to the 9, so it's 10 to the minus 9. So this is 2 times 10 to the minus 9 watts. The next one is 4 kilonewtons, so it's 4 times a kilonewton, and a kilonewton is 10 to the 3 newtons. The next one is 2 gigapascal, and a gigapascal, or a giga of anything, is a billion, and a billion is 10 to the 9. So that's 2 times 10 to the 9 Pascal. And then we come to the question, which is the one that we have to be careful with, and 5 micrograms, that's what this is, 5 micrograms, means 5 times 1 microgram, which is 10 to the minus 6 grams. But remember, the fundamental unit of mass is not the gram in the SI system, it is the kilogram. And let's remember that 1 gram is 10 to the minus 3 kilograms. It is 1,000th part of a kilogram. So therefore, we have that 5 micrograms is equal to 5 times 10 to the minus 6 times 1 gram, which is 10 to the minus 3 kilograms. And that is 5 times 10 to the minus 9, because we just add the powers here. Minus 6 plus minus 3 is minus 9. So it is 5 times 10 to the minus 9 kilograms. So those are our answers, and these prefixes are ones that I think people ought to know off by heart. As your careers develop, you are likely to find prefixes for larger and smaller quantities becoming used as technology becomes ever more sophisticated. But for the moment, we will stop at this and move on to the next question. So, in this question, we've been asked to convert three quantities written here into these units. So we're going to go from square millimeters to square meters, cubic centimeters to cubic meters, square meters into square kilometers. So let's do them one at a time. So 3 square millimeters. If we want to make the conversion, the number in front here is irrelevant. It just sits there. We do not in any way change it. So you can think of this as 3 times 1 square millimeter, or you could think of this as 3 times 1 millimeter squared. And you can see now what's going to happen, I hope. This just sits there, and we're going to convert 1 millimeter into 1 meter so that we can make this conversion, and then square that and then just multiply it by 3. So what we get is the following. We have 3 times, open brackets, and 1 millimeter, as we just discussed a moment ago, is a thousandth part of a meter, so it is 10 to the minus 3 meters, all squared. So this is 3 times, and now when we square the brackets, we square the number and we square the units. So 10 to the minus 3 squared, we just multiply the minus 3 by 2, so we're going to get 10 to the minus 6, and then we square the meters and get, of course, meters squared. So 3 millimeters squared is 3 times 10 to the minus 6 square meters, and that is our first answer. The second question was 7 cubic centimeters. So in exactly the same way, the 7 is just going to sit there multiplying everything, and it is 7 times 1 centimeter all cubed. So that is 7 times, and a centimeter is 100th part of a meter, so it is 10 to the minus 2 meters, all cubed. So this is 7 times, and now we cube everything in the brackets. 10 to the minus 2 cubed, it's minus 2 times 3, so that's 10 to the minus 6, and the units meters are cubed, and we get meters cubed. So 7 centimeters cubed, 7 cubic centimeters, is 7 times 10 to the minus 6 cubic meters. And the third question is to convert this into square kilometers. So we have 2.1 square meters. That's 2.1 times 1 meter squared. And remember that a kilometer is 1,000 meters, so 1 meter is 1,000th part of a kilometer, and it's 10 to the minus 3. So what we have here is 2.1 times, open brackets, 10 to the minus 3 kilometers, all squared. So when we square it, we have 2.1, of course, times 10 to the minus 6 times square kilometers. So that's 2.1 square meters expressed in those units of square kilometers. So practicing this is really important, because if you get these calculations wrong, if for example you said that you had written 10 to the plus 6 there, then you would actually be out by a factor of 1 trillion, because the ratio of your answer and the correct answer would be 10 to the 12, and that's a trillion, and we don't want to be wrong by anything as much as that. Okay, so let's look at the next question. So this question asks us to look at a density, and we're going to express the density which is given as 8 times 10 to the 3, so that's 8,000 kilograms per cubic meter, in grams per cubic centimetre. So this number is going to sit there until the end. If there are any powers of 10, we will tidy this up at the end. And these are the things that we need to change. So let's think first of all about what this means. What it means is that we have a density is 8 times 10 to the 3, so it's 8,000, and then it's kilograms, the number of kilograms for every cubic meter. So I'm going to divide here by cubic meters. And then to put this a little bit more simply, I'm going to say this is 8 times 10 to the 3, that's a number, times 1 kilogram divided by 1 cubic meter. And now all we have to do is to change these into grams per cubic centimetre, and we will have the answer. So we do this in steps. So we say that our density is 8 times 10 to the 3 times, and 1 kilogram is 10 to the 3 grams. So we want this in grams per cubic centimetre. We change the kilogram into grams. And if you have a kilogram, you have 1,000 grams, so we expect this to be a larger number, increasing the result. What about in the denominator? Well, in the denominator, we're dividing here by a cubic meter. So we're saying this is the density is the mass for 1 cubic meter of the substance. If we're now going to go to 1 cubic centimeter, then we have a much smaller volume and we expect the mass to drop. So I'm expecting to have a large number here on the bottom, a number that's bigger than 1, so as to make the answer smaller, because I would expect a smaller mass in 1 cubic centimetre. This has made the answer larger because we're measuring the mass now in grams, but the number on the bottom must make things smaller. So that's a sort of check that you can have that you've not made a mistake. So on the bottom, what we have is a cubic meter. So that we can think of, let's do this nice and slowly, as 1 meter cubed. So we have 8 times 10 to the 3 times 10 to the 3 grams divided by, and now we want to write this as cubic centimeters on the bottom, and a meter is 100 centimeters, so it is 10 to the 2 centimeters all cubed. And you see here we have a number bigger than 1, just as we hope to get. So what do we get? Well, we have 8 times 10 to the 3, so far that's just sitting there, times 10 to the 3 grams, and on the bottom, when we cube the brackets here, we cube this, 10 to the 2 cubed is 10 to the 6, you just multiply the 2 by the 3, so it's 10 to the 6, and centimetres cubed gives you, of course, centimetres cubed. So now, what we see is in the numerator, we have 10 to the 3 times 10 to the 3. That is 10 to the 6. On the bottom, we have 10 to the 6. They are all going to cancel. So that and that and that cancel. So our answer, rho, is going to be, the density is going to be 8 grams per cubic centimetre, but I'm not going to write it on the bottom here, I'm just going to write it as per cubic centimetre with a negative power. So that is our answer. If you get these things right all the time, you can speed up this calculation, but I would definitely break it down slowly, at least to this sort of extent, and think of it this way, so as to make sure that you get the right answer. With that, we'll move on to the next question. So in this final question, we've been given this expression, which is an expression for something called Young's modulus, and we've been given the various quantities that need to be put into it. But the first thing that you should notice is that the values of these quantities are not given in terms of the base or derived units. So this is not in meters, this is not in newtons, etc. So we could, and it would be a very foolish thing to do, put these numbers into the equation and then try and sort them out all together. And I think that is a very, very good way of making a mistake, which we don't want to do. So instead of that, let's not do that, and instead let's work out what these quantities are in terms of the SI units, and then we can do them one at a time, and it would be much simpler to just put them into the equation at the end. So what we're going to do is we're going to say F is 0.1 kilonewton, so it is 0.1, and the kilonewton is 1,000 newtons, and 0.1 is a tenth, so we can either say we're multiplying a tenth by 1,000 and it leaves us with 100, or we could say that we're going to take one of these powers out, leaving us with 100, and the power that we take out is a factor of 10, and 10 times 0.1 is 1. Whichever way you want to think about it, what we have is 10 to the 2 newtons. And the newton is the derived unit for force, and that can be substituted into the equation, and it will help us to get the answer correctly in terms of SI units. The next quantity that we need is L, and L is 250 centimeters. Now 100 centimeters is a meter, so we could say that 250 centimeters is 2.5 meters, or you could say that this is 250 times 10 to the minus 2 meters, and then when you multiply that out you get 2.5 meters. Either way, of course, you get the same answer. So that's the first two quantities that we're going to need to put into the numerator, and this is now in SI units. A is given to us in terms of square millimeters, so it is 0.1 times 10 to the minus 2 square millimeters, so that's 0.1 or 10 to the minus 1 times 1 millimeter all squared, and a millimeter is 10 to the minus 3 meters. It's 1,000th part of a meter. So what we have is, I'm going to write the 0.1 as 10 to the minus 1, and then we have 10 to the minus 3 squared, and 10 to the minus 3 squared is 10 to the minus 6, so that's 10 to the minus 6. 10 to the minus 6 times 10 to the minus 1 is 10 to the minus 7. So we have 10 to the minus 7 square meters. So in this last step again, this was the key step, going from here square millimeters to here square meters, and then we just multiplied the powers of 10 to tidy things up. And then finally delta x is 1 centimeter, and a centimeter is 10 to the minus 2 meters, because a centimeter is 100th part of a meter. So now we've actually done all the hard work. We have F in terms of a derived unit, L in terms of a fundamental SI unit, A in terms of fundamental unit squared, and delta X in terms of a fundamental unit. So everything means that we can just substitute these values into our equation, and the wonder of the SI unit system, or any good unit system, is that the answer will then be automatically in SI units. So what do? We say E is F is 10 to the 2, and that's going to be in terms of newtons. L is given to us here, 2.5, and that's meters. And on the bottom we have the area, which was 10 to the minus 7 square meters, times delta X, which is 10 to the minus 2 meters. And if we just want to try to tidy up the units and see how that works, well, in the numerator we have newtons for F, we have meters for the length, and on the bottom we have meters squared for the area and meters for the extension delta X. And what we see is the meters on the top and the meters on the bottom can cancel, and we have newtons per meter squared, and we just recall that newtons per meter squared are called Pascal. So all we need to do now is tidy up our answer here, and what we're going to find is that E is equal to, so we have 2.5 times 10 to the 2 divided by 10 to the minus 9, because we just add these powers together, and minus 7 plus minus 2 is overall minus 9. And now we say we're going to take these factors of 10 and tidy them. So it's 10 to the 2 divided by 10 to the minus 9. So we've got 2 minus minus 9. And minus minus 9 means that we are adding plus 9. So we're going to get 10 to the 11, 2 plus 9. So we have E is 2.5 times 10 to the 11 Pascal. But the question asked for gigapascal, so what we're going to have to do is to pull out a factor of 10 to the 9. So we say that E is 2.5 times 10 to the 2 times 10 to the 9 Pascal, and this is a gigapascal, and 2.5 times 10 to the 2 can be either left in that form, or you could say it is 250, which is what I'm actually going to do here. So E is 250 gigapascal. And the key messages from this calculation have been, at the beginning, sort out things like this which have been given to you in the wrong sort of units. Just tidy them up individually. Then you can put them into the equation, and the units will then always work. And at the end, if you get an answer like this and you want to use a prefix, or you've been asked to use a prefix to express it in terms of, say, in this case, gigapascal, then you just do that at the time. Just pull out the relevant factors of 10 so that you've got the answer that you are looking for. And with that, I will stop this podcast. I hope it has helped you.